The speaker today is Sourav Sarkar, and he contributed optical theorem for CFT and conformal Regge theory. All right, please go ahead.
Okay, thanks, Tom, and thanks for allowing me to speak here. So I will be presenting a new optical theorem that we have derived and how we apply it to study conformal Regge theory. It's based on this recent paper that we uploaded, and my collaborators are Antonio Antunes, Miguel Costa, Tobias Hansen, and Aditya Sarkar. So let's talk about the motivation first. So there are two main topics that we deal with in this project. So one is unitarity methods. In quantum field theory, the optical theorem is a direct consequence of unitarity, and we can relate, say, L minus one loop amplitudes to the imaginary part of an loop amplitude, and then we can use the dispersion relation to construct the full amplitude from the imaginary part. And the other subject that we'll be dealing with is Regge theory. So the Regge limit is the high energy limit of scattering processes. And so in this limit, we typically have to sum over some Regge trajectories on which we have particles of unbounded spin. So the broad theme will be to study these topics in the context of ADS CFT, and then we'll also relate them to flat space. So in CFT, we now have the analog. In CFT, the analog of the imaginary part of the transition amplitude is the d disk of a 4-point function. And we now have dispersion relations using which we can construct the correlator from the d disk. And we can also obtain the CFT data from the d disk. So in order to have unitarity based methods, one would want that we can calculate the d disk at a higher order from correlators or CFT data at a lower order. And let's say if we consider a correlator that we expand in the 1/n expansion, so there have been calculations where we take, say, the tree-level CFT
Sorry,
data and
sorry.
yes.
Maybe some people are having issues with audio. Is there's something in the chat? It says there's some. Actually, it sounds fine for me. Is it? Are people getting too much noise? People in the
I hear
chat.
fine.
It's okay.
Yeah, it's a little bit of noise, but I think it's fine.
Should I continue?
I guess it's fine for many people. Yeah. Why don't we keep going?
Okay, so I was saying that we can take tree-level CFT data and square it in some sense to obtain the D disk. And also we now have more diagrammatic unitarity methods that apply to Witten diagrams in the bulk and also Feynman diagrams at weak coupling. What we want to do is we want to take the tree-level correlators, and instead of going through CFT data, uh, we would like to glue tree-level correlators to obtain a one-loop correlator. And schematically, we'll take a single discontinuity of two tree-level correlators, implement some shadow transforms, and then the gluing will give us the double discontinuity of the one-loop correlator. Okay, so the next topic that we'll deal with is conformal Regge theory. In the bulk, so this is a particular kinematic limit of conformal correlators, and it corresponds to high energy scattering in the bulk ADS theory at fixed impact parameter. So I'll go into what these things are more in details later. So in the Regge limit, we can play around with the 't Hooft coupling and the center of mass energy. If we take the 't Hooft coupling to be large first and then take the energy to be large, then the graviton exchange dominates, and this exchange iconalizes in loop order. This has been shown. If we just take the energy to be large, then we have to consider we basically have to resum all of the leading Regge trajectories, all the exchanges, and that gives us the Pomeron exchange. And recently, what has also been done is that you first take S large, and then we take the 't-Hooft coupling large to, and this has been done to show the iconization in Pomeroy loops. So what we will do is we will apply the optical theorem that we derive in the Regge limit, and we will carry out this entire analysis in, say, what's called the impact parameter representation. In this representation, the optical theorem is multiplicative. So it allows us to more or less easily incorporate spinning double traces. And these double traces, they're usually, they are suppressed at large tooth coupling. And in other words, they correspond to all the string theory states that would couple to the Pomeroy and the dilaton. So we are basically considering this process here, the d-disk. In terms of a Witten diagram, we can think of this. And when we take the Regge limit, so the horizontal lines, they are Pomerans, and the vertical ellipses, so these include all string theory states that would couple to the Pomeroy and the dilaton. And then we show that, so these are called tidal excitations. And then we show that the tidal excitations can be packaged into what we call a vertex function in ADS, and VADS. And once we do this, we then take a flat space limit. We follow a prescription given by Kornalba, and we recover say, like the flat space optical theorem. And then we can consider concretely the scattering of 4 dilatons at one loop, at genus 1 in the Regge limit. The corresponding result in flat space type 2B string theory is known. And there too, you have the tidal excitations are described by a vertex function. And then, so this imposes, the flat space limit imposes some constraints on the vertex function in ADS. Okay, so now let's go more into the details. So first we talk about the perturbative optical theorem. So let's first start with expanding a correlator in conformal blocks. And we can do that with the projector here. This S of O is the shadow transform of O. So when we expand it in blocks, we can represent it, if we insert the projector in the correlator, we diagrammatically will represent it in this way. So this point is integrated over the black point. So this diagram here, it represents a gluing of two 3-point functions, and then we have to take a projection to get rid of the contribution of the shadow operator. But when we are doing the sum over the overall block, so we include both single traces and multi traces. The idea, so right now I'm just trying to motivate the gluing formula or the optical theorem. So, and the idea is that we use conglomeration to replace the sum over double trace operators with a double sum over single trace operators. So instead of having this projector, like the sum of these projectors over this particular family of double trace operators, we replace it with one single projector which has two integrals instead of one integral, and we just summed over the double trace operators, but when we insert this projector, we'll have a double sum over the single trace operators, and this holds at leading order in 1 over n. So in this picture, say we had a gluing of 3-point functions to begin with, where this exchange is double trace, but now using conglomeration, we can replace it with two gluings over single trace operators, and then we have to sum over O5 and O6. So what this gives us is that we have a gluing over two 4-point functions. So each one here is a 4-point function. And in the end, we have to again do some projections to remove contributions from shadows. And at leading order in 1 over n, it turns out that we only see contributions from the external double traces, the O2. But we want to also look at the contributions from double traces that are distinct from the external ones. So to do that, we'll take the double discontinuity on both sides, and on the left side, on the right hand side, this will factorize into the single discontinuity of individual correlators. So roughly, this is the kind of relation we want to derive, that the d-disk of the correlator at order 1 over n to the 4 is given by a gluing of two single discontinuities, each of which is at order 1 over n square, and we do some we shadow transform two of the operators for one of the tree-level correlators. Okay, so now let's look at the derivation briefly. So we use a lot of machinery from a paper by these guys, and all of this calculation works for general spin, but I have not I've suppressed all indices to reduce clutter. So if we take, let's take the partial wave expansion of the correlator, and then if we apply with the shadow transform on say two of the operators, then the spectral function, then the shadow transform correlator has this expansion, and the spectral function is related to the original spectral function with these two coefficients s. What this coefficient is it gives the action of shadow transform on 3-point structures. So in general, if we take a 3-point structure, this A here, it denotes, uh, I mean, we have many tensor structures. So let's say one particular one of those. Now, when we act with the shadow transform on one of the operators, in general, it will give me a combination of multiple structures, and the S, this coefficient or this matrix, it gives a map between these two bases of structures. So now that we know the partial wave expansion for the correlator and the shadow transform correlator, let's use that in the gluing. So let's consider this gluing, and so we'll use the partial wave expansion for each of them, and that gives us an integral over these two partial waves. And this is basically a bubble integral. So if we do this bubble integral, then we get another partial wave just from for the external operators, and the two operators here, O and O prime, they are fixed, forced to be the same one, and there are a bunch of constants flying around which we don't want to look at right now. So if we plug those results back into the gluing, this is what we get. So we have one single integral now because of the delta function, and we have one spectral function each from each of the two correlators here, and this Q is all the S coefficients and other 3-point pairings and everything. We package that and call that Q, and we have a partial wave. So we don't want to, I mean, we don't need to see what Q looks like here, but an important property of Q is that it's the inverse of the mean field theory spectral function, which was derived in this paper. And this is kind of the main property that simplifies this integral here. So if we take the mean field theory case where each of the I is from a mean field theory, then one of the I's just cancels with the Q, and then we get back a mean field theory correlator. But in general, we can take the residue of this, like we can evaluate this integral, take the residues at the double traces 5, 6, and then we see that is equal to the residue of this spectral function at those same double traces, and that gives us this result, that when we glue two of these correlators, and that's true, sorry, so this is true at leading order in 1 over n. So if we glue two of these correlators and then look at the contribution from the 5, 6 double traces, then that is equal to what it would have been if we had just expanded this and considered the contribution from the 5, 6 double traces. So in terms of Now there can be these 5 operators, 5 and 6 can also be equal to the external operators, or say 5 can be equal to 1 and 6 can be equal to 4. So there are two distinct cases when this 5 6 is equal to one of the external pairs, which represented by the two diagrams on the left, and the other case when they're distinct. So when they are equal to one of the two pairs, then one of these two correlators at leading order is a mean field theory correlator. So let's say this number in the blob represents the leading order in 1 over n. So these diagrams start showing up at 1 over n square, but when 5 and 6 are distinct from the external operators, external pairs, then that shows up at 1 over n to the 4. But we want to include this too. So we will apply with the double discontinuity to push all of these, to push all the terms to order 1 over n to the 4. So in order to take the double discontinuity, we let's say we assume a certain kinematical configuration that O4 is in the future of O1 and O2 is in the future of O3, and then we can weak rotate these points with different values, relative values of epsilons to, and then we get four orderings, and then we can package them into this double discontinuity. And on the right hand side, each of the so one correlator depends on 2 3 and the other correlator depends on 1 4. So we get these single commutators, and the single commutators are equal to a discontinuity of the correlator, which will be given, which is defined by this. So we take the pair that has the commutator, we take that distance and we rotate it by half, half a circle, and then half a circle in the other direction, and the discontinuity is the difference. And the important thing is that, I mean, the useful thing is that this discontinuity has easy action on the T-channel conformal blocks. So what it does is that, let's say if we take the discontinuity here and we expand this in conformal blocks, so taking the disk will give me a sign, and taking the d-disk will give me two signs. So let's take the case when the exchange is distinct from the external double trace operators. So then the sign is finite, but one of the OP coefficients is necessarily a non-mean field theory OP coefficient. So we get a factor of 1 over n square from that. So this is the case which was at order 1 over n to the 4 but the exchange can also be equal to external double traces, and in that case this started, like, the leading order was order 1 over n. This was order 0, yeah, at leading order. But now, because of the sign, we have an anomalous dimension here, which comes at 1 over n square. So both of these are at the same order. So in terms of the diagrams now, so this was at order 0 and this at order 1. But because of the anomalous dimension now here, both of these are at the same order. And so all contributions are at order 1 over n to the 4. Oops, sorry. So now if we think about the result that we had earlier, so if we take, furthermore, so one more thing I forgot to mention. So each term here, so in general, when we are taking the residues, we have contribution. We could have taken residues at operators which are different from double trace of 5 6. But each term here already comes with an explicit 1 over n square. So the leading order contribution will only be from O being equal to the double trace of 5 6, so that it can be a mean field theory OP coefficient. So combining all these facts, if we apply it to the result that we had before taking discontinuities, we get this optical theorem that we wanted to derive, that we take this discontinuity of tree-level correlators, and then we glue it with these shadow transforms. And if we project, we discard the contribution from shadow double traces, And if we sum over all the single traces, then we get the D disk, the contribution to the one loop D disk from all double traces. So this is the perturbative optical theorem that we wanted to derive. So yeah, this is the result. Now next what we'll do is we want to apply this result to conformal Regge theory. But first, let's briefly uh, go through the Regge limit. So we can arrange. So the Regge limit can be described from in this diagram. So we have arranged all these points in the central Poincare patch. These two pairs are time-like, and all other pairs are space-like. And the limit is basically that we send, say, the pair y3 and y4 to light-like separation coming from space-like separation, and similarly for the other pair y1, y2. And in terms of cross ratios, we have to we can start with the Euclidean correlator, and then continue. We keep z fixed and continue z bar anticlockwise around 1, and then take both z and z bar to 0 while we keep the ratio fixed. But what we'll do is we want to parameterize the points in a different way, because this allows us to go to the impact parameter representation more easily. So we'll parameterize each point with these Poincare patch coordinates, like each point, and in the Regge limit, each operator will go to the center of its own Poincare patch in the longitudinal directions. And in this limit, it has been shown that the correlator, it depends only on the difference between x1 and x2, and or the difference between x3 and x4. So once we have that, we now want to do this Fourier transform, and that takes us to the impact parameter representation of this CFT correlator. The S has the interpretation of center of mass energy, and the L, defined in this way, has the interpretation of impact parameter in ADS. And the Regge limit is that we take S to be large while we keep L finite. Now, when we apply the Regge limit to the block expansion of the correlator, or the partial wave expansion of the correlator, we see that we have to include the contributions grow with spin, so we have to include all high spin terms. And if we do the Sommerfeld-Watson resummation over the leading Regge trajectory, we get the Pomeron. And then the impact parameter transform is of this form, and the omega here is a harmonic function on the transverse hyperboloid in ADS. So with that background, okay, now let's see how we can apply the optical theorem in the Regge limit. So we had a gluing of two correlators. So what we assume is that in the Regge limit, each of the three level correlators is also in the Regge limit. And this would mean, this would mean the following this configuration that we show in this picture for the three level correlators. That yes, so now y1 and y7 are these pairs that approach light-like separation, and y4 and y8, and similarly for the other correlator. So what we want to do now is that we want to also analytically continue. So 7 and 8 are like these might appear to be new points, but these are basically because of the shadow transform. Like I'm shadow transforming 7 to 5 and 8 to 6. And now in the optical theorem, we also rotate the points 7, 8, and 5, 6. And we do it such a way that we put 7 and 8 to time order and 5 and 6 to anti-time order with respect to this configuration. So we get these commutators of Lorentzian correlators. And these correlators now define these discontinuities that can be evaluated in this way. So this commutator is basically the difference between the correlator on the Regge sheet and the correlator with a
Sorry,
mix. Yes.
ask a question.
Yeah.
Maybe it's a stupid question. So point 5 and 6 are integrated. So why can you choose the configuration also for those guys?
It's an assumption. It's an assumption that the leading contribution in so earlier they were integrated, but it was not in the Regge limit. But we are assuming here that in the Regge limit, the leading contribution comes when the points 5, 6 are also such that the correlator in the Regge limit. This makes
Okay, but
sense physically, and also it's probably easier to explain it with the impact parameter representation why it makes sense. So maybe I answer it in the.
okay, cool, thanks.
Okay, so I was in here. So this discontinuity is the difference between the correlator and the Regge sheet and the correlator with this mixed ordering, which is in the Euclidean sheet. And in the Regge limit, the correlator on the Regge sheet dominates. So it's discontinuity is approximately equals to this Regge sheet correlator, and the other one is equals to the minus Regge sheet correlator. And now in these Poincare patch coordinates, because we assumed each of the correlators to be in the Regge limit itself, we can also use the dependencies also on these differences that are almost slightly separated. And these are basically the discontinuities here. So if we in terms of the diagram, it's as follows. So let's imagine, so this is the Witten diagram, and the horizontal lines are Pomerans, and we cut the vertical lines, and this will give, and this gives us discontinuity of two correlators, and the vertical lines are correspond to spinning double traces or generic double traces that may not be equal to the external ones in CFT. And in string theory, they can include in general all states that couple to the Pomeron and the dilaton. And okay, let me maybe just justify why it's okay to assume the Regge limit is because so in the Regge limit, each correlator comes with this power of s to the spin of the Pomeron minus one, and on the left hand side it's like j nu one plus j nu two minus two. So that power can be achieved only if each of the correlators come with the maximal power in s. So that it's not a proof, but it justifies the assumption that each of the individual correlators on the right hand side are in the Regge limit. So now we want to take the Regge limit optical theorem to impact parameter representation. So on the left hand side we had the d disk, which in the Regge limit is equal to the sum of these two Regge sheet correlators, and them being related like by complex conjugation, it gives us the real part of the B. This is like the phase shift. So, and on the right hand side each of them go to the B. So we had a bunch of position space integrals, but the Fourier transforms and the position space integrals, they all canceled each other out, and we get a purely multiplicative formula. And of course there are index, like there are tensor structures here, and the indices are contracted across these two correlators, but we keep that implicit. So what we now want to do is, when we have tensor structures, how do we, and so we have these contractions across the tensor structures, we want to know how we can simplify that. So in general, so this is the impact parameter representation when two of the legs are dilatons, but the other two are some generic spinning operators. So in the Regge limit, it takes the following form. So I have s raised to this Pomeron spin, and I have this beta is now the beta for this case, which we don't know in general. The the tensor structures themselves we generate from differential operators that we construct in this way. So that they're constructed from the unit vector P and derivative and covariant derivatives in P, and also the unit vector P hat and covariant derivatives in P bar, P bar hat, and yeah, in P bar. And because we will be gluing two of these, we multiply two of these, we have two omegas. So in general, we have two omegas, we have some differential operators acting on those omegas, and then we have a sum over the spectrum. So the product of two omegas, we can express it with an integral as an integral over 1 omega with this function. And then we also have terms which are some derivatives acting on 1 omega and some other, and derivatives acting on the other one, and they are contracted. And these we can calculate exactly by acting with the Laplacian on this line, and then we get that it's of this form. We act with the Laplacian and then use the fact that omega is the harmonic function on the transverse hyperboloid. So we get this form that we can always write these contractions in this form, where wk, this is a polynomial of with a maximum order as shown here. So we can calculate all the wk inductively. So now we can plug it back into the, so what we did here is that we exchanged the index tensor structure contractions for some polynomials and an integral and one more integral new here. And now we can plug it back, and when we sum over the spectrum, we define the result to have this form that so we have some beta of spinning ones, and then we have the W case, and then two betas actually. And then when we sum over, we propose that it has the following form, that we have a product of the two scalar betas times a V, which takes care of all the spinning contributions. Because, and this makes sense because this V is 1 in the large Tooft coupling limit, when the only contribution that would matter is the scalar ones, because we took the external particles to be scalar, and in the last Tooft coupling limit, the exchanges that dominate is when the exchanged operators are equal to the external operators. So if we take this limit, so this limit was studied by Melzer and he used the Lorentzian inversion formula. So if we take this limit on this formula, then we can recover the results that he had derived. Now that we have this formula, we want to take the flat space limit of this equation, and that will allow us to constrain some dynamical quantities. So, okay, but briefly, so in flat space, the Regge limit is, let's say we take large S and finite T, and then we sum over the leading Regge trajectory, and we get this Pomeroy propagator. And the optical theorem is also the same, it works in the same way, that we cut the vertical lines, and these include sum over all states in the string theory that could couple to the dilaton and the Pomeroy. The impact parameter representation in flat space, it gives us the phase shift. The impact parameter transform is a Fourier transform over the transverse directions. So this delta is so the b that we had from the impact parameter transform in ADS is the ADS analog of the flat space phase shift delta. And we can also show that the optical theorem in this impact parameter space in the Regge limit in flat space also takes this multiplicative form, which is, and the one in ADS was exactly of the same form. And in this case, we can also, in this case, like yeah, so these calculations were done long time ago, so we can package the contribution of all the this the spinning exchanges in this vertex function, which is a sum over a product of these 3-point amplitudes. And in position space, in momentum space, so this multiplicative form is in impact parameter space, but in momentum space, the optical theorem would look like this. So we have the Pomeron propagators from the dilaton, like when all the external operators are dilatons, and then we have the vertex function, which accounts for all spinning exchanges in the vertical lines, for all the massive string theory states. And yeah, so now let's see how we exactly take the flat space limit. So this flat space limit prescription, it works in the Regge limit. It was given by Konalba. So we scale the variables in this way. So if we follow this prescription, then we can already see that certain kinematical quantities go to the corresponding ones in flat space. For example, in flat space, we had these integrals over the transverse space, but the integrand mostly depends. The integrand depends. The other quantities that would be there in the integrand, they depend on the magnitude of q. So we want to evaluate the angular integrals, and that gives us this harmonic function, and then we can check explicitly that the ADS one goes to the flat space one if we follow the prescription here, and also. And also a product of two can be expanded in the same way with a function phi, and the ADS phi goes to the flat space phi. So at tree level, if we apply all this, the prescription and the results for the kinematical quantities, then we propose that B, it goes to I times the flat space delta, and the d nu integral goes to the integral over mod q. And so this beta nu here is a dynamical quantity, and if we impose that the flat space limit goes to the Pomeron propagator in flat space, then this serves as a constraint on beta, and this has been already imposed in the literature. And similarly on the Pomeron spin. So yeah, at tree level, if we impose the flat space limit, then we get the following, then we get these constraints on the two dynamical quantities here. And we can similarly work out the case of tree level correlators where two of the external operators have spin. It's just a bit more technically complicated with the tensor structures. But those, if we do that, then we also constrain the beta for those spinning correlators with the beta in flat space for the tree level correlators. Okay, so mainly what we did is we calculated this one loop, the one loop expression in the Regge limit for dilaton scattering, and so this part is just the optical theorem in impact parameter space, and then we showed that it can be written in this way here in terms of the new integrals. And correspondingly in flat space, this is again the flat space optical theorem, and this can be, if we earlier I had the integrals I had shown were integrals over q, but if we do the angular integrals, it can be written in this form. And now we can map each quantity to its flat space analog. So because B went to I delta, so the real part of beta 1 loop here goes to the imaginary part of delta 1 loop, and this one goes also to the flat space limits. The sum over polarizations here is taken care of by the index contractions across the two B's, and same for this result. And here now we have an additional constraint on the ADS vertex function from the flat space vertex function, which is known, which was calculated by Amati, Shafaluni, and Veneziano. So I will briefly describe how we can exactly implement the constraints. So let's say let's say we have this function, which is a function of both nu and lambda. If we assume that a gravity limit exists, then we can write it in this expansion. And then if we assume that a flat space limit exists too, that for a given term here, corresponding to a given power of lambda, it limits the maximum power of nu it could have. If it were any higher, it would blow up. So Fn is limited to, is constrained to be of this form and have this maximal power. Now when we take the flat space limit, these other terms here will go to 0, and the flat space limit will be of this form. And this quantity nu square over root lambda, it will go to t, which is q square minus q square in flat space. So this sum with these coefficients, which are dynamical inside in the CFT or in ADS, this equation, this sum is equals to this flat space quantity. If we know this, then this solves as a constraint on these dynamical quantities. So by taking the flat space limit, we basically impose a constraint in this manner on the Pomerance spin and the propagators and the vertex function in ADS. For example, this is known in flat space to have this expression, and that already tells us that in ADS, the vertex function for 4 dilaton scattering at genus 1 in type 2b string theory, it should be of this form plus terms which vanish in the flat space limit. Okay, so now I think I can conclude. Okay, so to summarize what we did, so we first started with a perturbative optical theorem in CFT. So in this theorem, what we did is we took two single discontinuities of tree-level correlators, and then we glued them with some shadow transforms. And then if we sum over single trace operators, we get the contribution to the double discontinuity of the one loop correlator from the double traces. And then we applied this optical theorem in the Regge limit to study a 4-point function of pairwise equal scalars. And in the impact parameter representation, it takes a multiplicative form, which allows us to incorporate more or less in a simple way the contribution from generic spinning double trace operators. And concretely, we can then think of this as the scattering of 4 dilatons at genus 1 in ADS string theory in the Regge limit. The contributions of all the tidal excitations, they are packaged into this ADS vertex function. And so finally we follow this flat space prescription in the Regge limit, and what that allows us to do is it constrains the dynamical quantities appearing at tree level and at one loop from the corresponding quantities in type 2b string theory in flat space, which are known. So in the future, what we didn't do so far, we should try to apply the optical theorem to some concrete examples to actually do the gluing those integrals and try to apply it to, say, holographic correlators. And there has been other work on optical theorem for, say, Witten diagrams, and it will be good to understand how our optical theorem is related exactly to those. And then the one more question that we should answer is that when we took the optical theorem to the Regge limit, we really, the form that we presented really assumes the Regge limit, but we would like to ideally derive a Lorentzian bluing in general that is away from the Regge limit. Because we can keep lambda to be finite in the Regge limit, we can keep lambda to be finite in say the multiplicative optical theorem that we had. We think we can try to apply it to say n equals for superangles at weak coupling, and also it would be interesting to say we consider the one loop process. We could think of generalizing it to higher number of Pomeron loops. Okay, I think that's all from me. Thank you.
Thank you.
So I have a question. Can I ask?
Yeah.
Okay. So normally when we do the square in the traditional way, that we take the OP data at 3 level and we obtain the one loop from those, sometimes we need to solve a mixing problem, especially in n equals 4. So does your procedure somehow bypass this procedure?
I mean, so when we applied it to the Regge limit, we did not really, because we don't know. So the states that will appear in the optical theorem are states that have no R charge, and they are like they map to massive string states in flat space. Like they are states with no R charge, and the dimension grows with lambda, and they map to massive string states. But we don't know in general what these are. So I think the problem you are saying is not here. We don't have it here.
If you want to apply
Does it
n equals
answer your
4,
question?
you will have this problem. I said, if you in principle want to apply it to n equals 4, you will have this problem.
I mean, we are okay. I mean, we always cut lines with no R charge. So
Can I perhaps follow up on that?
yeah.
So quite early in your talk, maybe 15 minutes in, you had this expression where you had this anomalous dimension of like a mean field theory operator.
Yeah.
I mean, this is the place where you expect it to be a degeneracy if you're looking at n equals 4, for instance, or a generic theory with interactions, really. So how does that term propagate through your computations? Like, would you need to...
No, we don't really
term?
see it so far because we didn't really do the sum. Right? We don't like so far. We didn't do the n equals to superangles calculation, and the calculation that we didn't really do the sum because we don't know the spectrum. Like if we let me just go. So here, let's say, or even so here we have this sum, and we are not doing this sum because this is in general we don't know the spectrum in the ADS string theory. So we are not doing the sum as such. We are proposing that when we do the sum, because we can trade the tensor contractions for some polynomials, if we do the sum, then we can write it in this form with a vertex function v, which contains the information from all those exchanges, but we don't know what v is because we cannot do the calculation. But we can only, then what we do is we take the flat space limit, which only put some constraints on v. It constrains a part of v that has a non-zero flat space limit. But in general, we don't know what v is, and we don't do the sum, so we didn't see this problem so far.
So if you try to apply this to n equals 4, you would would multiple of these operators that mix contribute to this V, or would you single out a specific one of them?
I'm not.
Can I make a comment?
Yes, please.
So I think if you do this, the computation that Sourav showed was this formula in the box is general. But then the specific case was that strong coupling. As he said, it's more difficult to trace what are the operators. But at weak coupling, the computation that we have not done, I think we can do it in n equal to 4 supreme mules. I think we should choose the operators. You can choose some protected operators as the external ones. But then I think you'll have to use to solve mixing problems, because the operators that are exchanged then, the O5 and O6, the double traces that are exchanged then, those will acquire anomalous dimensions, and yeah, this problem will have to be solved order by order in lambda in the N-Mills coupling to check if this optical theorem is true.
Can I also make a comment? I mean, I think the question is about the optical theorem, and there, if you know the discontinuities of the tree-level correlators, then you don't need to solve a mixing problem, because you don't have to sum over double trace operators. You just have to know all the discontinuities of the tree-level correlator.
Sorry, are these tree-level correlators also including the double traces or not?
No, they have only single traces, but you have to sum over all of them. But there are the sums over n and l you don't have anymore. So normally you sum over all the double traces of all the pairs of operators. Now you just sum over the pairs of operators.
Correct me if I'm wrong. The number of 4-point functions that you need to actually write down is the same as the one you would have to write down to solve the mixing problem, but you don't actually have to diagonalize any matrix. So somehow this process is done automatically by your optical theorem. Is that correct?
Yes, I think so, yeah. It's the same data, but it's in a different form.
Okay. Cool. Thanks.
It's in the form of correlators, not double trace OP data.
Further questions? I guess not. So let's thank Sourav again. Thank you.